This musical keyboard is made out of a Möbius strip. The two ends are connected after flipping at 180 degrees. Unlike a piano, each key on this instrument plays two notes at a time, so these rhombuses that you see are really a stretched out grid of keys. One of the cool things about a Möbius strip is that it only has one side. If you walk along its face, you'll first walk through the opposite side, and then end up where you started. In other words, things wrap around as their own mirror image, and this instrument takes advantage of that. Along the diagonal is a chromatic piano keyboard. Once it wraps around, it starts going on the other diagonal, so to play the chord you want, just find one note on this keyboard and the other on this one. The key at their intersection will play those two notes. You have to be careful not to get confused though, because they're both the same keyboard. As arbitrary as it might seem, I did not just make this because synthesizers are cool and Möbius strips are cool. There's good mathematical motivation for making this thing, and I think it'll give you a new appreciation of topology and a new appreciation of music theory. Say that you're trying to control a robotic arm, and yes, this is still a video about Möbius strip pianos. We'll make it a simple arm that just has a shoulder and an elbow, and each can move between 0 and 180 degrees. In order to visualize all of the positions that this arm can be in, something you might do is say, well, we have two variables that control the whole system, so we'll use a 2D space like the XY plane, and then we'll pick one number for the angle of the shoulder and one number for the angle of the elbow, and that point gives our arm's position. Every point in this space corresponds to a configuration of the arm, so we call it a configuration space. Again, this example is two-dimensional because there are two variables, but if you're working with something more complicated like an animated character or transportation robots in a warehouse, your configuration space might have many dimensions. Let's try to find the configuration space of all musical chords, or to start off, all two-note chords or dyads. Just like our robotic arm, this system has two variables, so we'll need a 2D space. Pick one note from each keyboard and you have a chord. But unlike our robotic arm, which didn't have joints that could wrap around, if you continue going up or down from a musical note, you'll reach an octave, which we perceive as being effectively the same note. So this point here should map to the same dyad as this point here. But we really want a one-to-one mapping. So what we'll do is tape the two ends of our space together so that they wrap around. Of course, the other note also wraps around, so we tape those sides too. If you've been trying to follow what this shape would make if our space was a piece of paper, it would be a donut, a torus. But there's something we're missing. See, right now there are 12 notes in an octave, so our torus represents a total of 12 times 12 is 144 chords. But there's not that many, because C and E is the same thing as E and C, so we really should only have that's n times n plus 1 all over 2, so 78 possible two-note chords. The ones that are repeats are across this diagonal. So we'll cut off half of our space, or rather we'll fold it over. Once we do that, the sides that we have to tape are no longer the opposites, because they're not there. Now we need to tape these two adjacent edges. Naively, you might think that makes a cone, but notice the direction that we have to tape them. We need to flip it before taping, which isn't really easy, so we'll first make a cut here, then tape these two edges. Then remember to retape the part we cut, and that is a Möbius strip. The configuration space of all two-note chords is a Möbius strip. Now, this result is not unique to music. In general, the configuration space of two unordered points on a circle is a Möbius strip, and it happens that musical notes act the same as points on a circle. This result's application to music is also not something I came up with. You can find Dmitry Tymosko's paper on it in the description. Although I think I might be the first person to make a physical instrument out of it, albeit not a very practical one. If this gets worked out and turned into like a good playable instrument, maybe with like pressure sensitivity and a continuous touch screen so you can play vibrato and like control the pitch and stuff, I genuinely think that this would be an extremely cool way to make music. And it helps educationally too, to understand how chords fit together and how voices move. This prototype is made out of paper and aluminum foil with a layer of packing tape over it to act as an array of capacitive touch sensors. This uses a similar concept as touchscreens on phones. The idea is that two adjacent conductors form a capacitor and can store charge. So your finger, which is filled with water, will form the other end of a capacitor with this piece of aluminum foil and make it take longer to charge or discharge. I would have liked to use a microcontroller that can act as a USB device, but I was working with what I had on hand, so instead the aluminum foil sheets are connected to an Arduino Nano. And then I have a Python script on my computer that reads the serial port and sends MIDI messages when a key is touched. If you wanted to, you could maybe connect it to a software synthesizer and play whatever sound you want, but I was satisfied with the default Microsoft GS wavetable synth that comes with Windows. Its selection of 128 general MIDI instruments will be very familiar to anyone who's ever owned an inexpensive Casio keyboard or something like that. My Arduino doesn't have enough inputs to make one key for each of the 78 combinations of notes, so I chose a pentatonic scale, which has 15 possible chords. Instead of the traditional pentatonic scale, I chose one with E, F, G, B, and C, partly inspired by the nice combinations of chords that you get, partly inspired by the Pelog scale in Javanese gamelan music, which I think sounds nice. Because really anything conductive will act as a capacitor, it was kind of finicky getting this thing to work. Touching my laptop when I'm nowhere near the instrument changes the values. Plugging my computer into the wall, of course, turns my entire apartment into a capacitor. And all the wires and breadboard connections and strips of foil are forming capacitors with each other, so the instrument will sometimes play the wrong note. But I was able to figure out the code so that it mostly works. I think it's doing the best it can without making it out of something other than paper. Let's look at some patterns that you'll notice if you try to play this instrument. For starters, the keyboard along the diagonal plays every chord that includes C. Similarly, any diagonal contains all the chords with a certain note. The places where two of the same notes meet will always be on the edge, so that's how you play a scale. Moving along a horizontal line gives all of the pitches that form one interval, so top is unison, then minor second, major second, and so on, until it reaches the center, where we start to see their inversions. There's all kinds of beautiful symmetries and optimizations in the way that we write music that become clear when you look at how to play a song on this Möbius strip. I'll end this video by showing you what I mean. What's a song that heavily features two-note chords? Maybe the Rugrats theme song? Okay, maybe not. We'll look at Clair de Lune instead.